composite. And this is the chemical structure that we're saying right here. That right. This right here is the epoxy resin, and these are the epoxide groups on the ends right here. And this is the curing agent, and these are the nucleophilic sites right here. These sites right here will attack these oxygens right here, open up this ring, and then you're left with this type of structure. And so basically all the blues attack the reds, and it's just it's a chain reaction, and it happens throughout the entire composite, and it happens until it solidifies. So basically you start off with two liquids, they start cross-linking, you're left with a plastic-like substance. All right, a little bit about nanocomposites. Nanocomposites are composed of two or more materials that have different physical or chemical properties, with one being at least in the nanometer scale, nanometer being 10 to the negative 9 meters. Nanofillers such as halloysite nanotubes, carbon nanotubes, and other nanomaterials are desirable because they have superior physical and chemical properties. At the nanometer scale, they stop behaving like their bulk properties, and they have stronger special properties at the smaller scale, so we're trying to exploit that. Like I said, nanomaterials are incorporated into the epoxy to enhance the properties of the composite. All nanomaterials are purified and dispersed in an epoxy-compatible solvent prior to integration. Basically, we try to get the nanomaterials as pure as possible, and then try to get them as dissolved as possible, and then try to get them as well dispersed into the epoxy as possible. All composites in this research will be epoxy-based, using the epoxy I mentioned before, and we'll have halloysite nanofillers of various weight proportions. Halloysite introduction. This picture here on the background, that's basically what we're using. Halloysite has aluminum, silicon, oxygen, and H2O molecules. They're inorganic, but they're inorganic, but they're naturally occurring. It's basically a clay. They have various lengths and diameters. The diameters vary from around 15 nanometers. This is wrong right there. The lengths are around 100 to 1,000 nanometers. The mismatch in periodicity between the oxygen sharing leads to a tetrahedral silicon oxide sheets adjacent to octahedral aluminum oxide sheets, leading to the form of a tubular halloysite nanotube covered with hydroxyl groups. So basically, as you can see right here, these are the aluminum, the hydroxide groups. These are the white ones are the oxygen atoms, and then these are the inner silicon atoms. And basically, their structure leads to they just wrap around each other in different layers. And the distance between the layers in here is like on the order of like 5 to 10 angstroms. Like they're very small, they're very tightly packed. This is a better picture, a little more colorful. This one right here on the right is the type that we're using. These are two different types. And so basically these right here are oxygen like hydroxyl groups. And so the first part of our research, we actually we heat them up to burn these off. And then we try to attach things to the outside of them, and we try to attach or put stuff in the middle of them right here. And these two vectors right here, there's actually 3 types of these tubes, and they're based on the position of these vectors. So if they're rolled perpendicular to each other, you'll get one that's just a straight one. And then if you, at this angle right here, I forget what the angle is, you end up with one where you have chirally attached molecules. And then if the angle, I don't remember the angle off the top of my hand, but if you're above that angle, you get what's called a zigzag. So if you follow the oxygen molecules, you'll see a zigzag. If you follow them on the other one, you'll see an armchair. And if you follow them in the perpendicular one, you get a straight chain of molecules around. And that also affects the properties.
Perpendicular is better.
Yeah, perpendicular is better. And yeah, you get a more rigid structure. But like the same is true for carbon nanotubes. And on those, you actually want the zigzag one because the electrons can flow. They have a less impeded flow. But on this one, we want the straighter one so they're more rigid. These are some images of the nanotubes. This one's on a scale of, right there, right here, 4 microns. So it looks like a fiber right there. This is a little more zoomed in. This is actually a 15,000 K or 1500 K zoomed in. And they're just small, very tiny tubes. These are transmission electron microscopes. So you can kind of see the hollow tube on the inside. They're just tiny, very tiny hollow tubes. And this is extremely zoomed in. This is on the scale of 10 nanometers. So this is the wall of the nanotube. This is actually the inside of the nanotube right there. Recent work, what we've done, we've prepared now we've prepared 3 samples of pure epoxy, and then we've also purified the nanotubes. And we've made a sample with the nanotubes in the epoxy, and we've also done some mechanical testing. This is the actual process that we did. We're more specific, but we weighed out the curing agent in the resin to 24 to 100 ratio by weight. We diluted it with acetone. We stirred it. We used a rotary evaporator. Acetone boils at 57 degrees C, so we mix it under heat, and all the acetone is dissolved. We have silicone mold that we pour into to have a uniform shape, and then we cure it at 80 degrees for an hour and a half, and then 150 degrees for an hour and a half. We did come up with some problems. We had a lot of bubbles and trapped gas. What we plan on doing is using less solvent and degas it longer. So basically what happens, the more vigorous you're mixing, the more gases getting trapped, and the more solvent you mix in there to make it thinner, the harder it is to evaporate all of it, so you get what's called solvent entrapment. And so when you're curing it, the solvent's actually boiling while it's curing, and the epoxy is hardening, so you end up with these little air pockets, and that obviously makes it very weak.
Are you measuring like the rates of how fast they cure or how fast they harden?
Right now we're not. There are computer models that we follow where they actually simulate, like 10,000 atoms or 10,000 molecules of the epoxy, and they do the curing rate through there, and then from there they get like what's the best curing time and the curing ratio. But we're not actually measuring the ratio, the rate of the curing at. We just monitor the temperature and the time. The second sample, basically the same thing, except we degassed it longer. And degassing, basically, we put it in an oven, we put it under vacuum, we lower the pressure as low as possible, and so it induces a boiling and evaporating, and it just basically sucks all the air out. Concerns. The temperature at which we degassed it was kind of high. It's kind of close to the curing temperature, so we don't want any premature curing. But at the same time, if we lower the temperature, the mixture becomes very viscous, and it's hard to get any bubbles to come out because it's so thick. So we want a higher temperature, so it's a very fine line we're trying to figure out. Our samples with the nanotubes in them, this is the process. Basically, we purified and weighed the sample. We sonicated them, basically like a jewelry cleaner, just very high powered. And so it shakes them up, gets them really dispersed, and then we mix them into the epoxy. The rest of the procedure is exactly the same curing time, same temperatures, same degassing periods. We had some concerns. As soon as we mixed it, we noticed an immediate color change. And these nanotubes, they're naturally found in the earth, so they have a lot of impurities. And we think there's iron impurities because of the color that we saw. But we're going to do some FTIR testing and some XRD testing to see what molecules are actually in them. This is some of the mechanical testing. This is where it gets kind of interesting. We're looking at right here, this one's the Young modulus. And this tensile strength, maximum strength, load at breaking, tensile stress. So basically we have a machine that pulls them at a rate of 5 millimeters per minute, and we have a 1,000-pound sensor. So it pulls them very slow, it measures at what rate they're being pulled and what rate they break. And that's where a lot of the math, the software does it. Like it calculates Young modulus, elasticity. I should have put the equations on here, but yeah, this is where all the math comes in, and we leave all that up to the computers because it does a whole lot of math and it spits out all the information to us. But one of the interesting things, these numbers right here should be higher. I mean, these are decent ratings, but just as a basic, they should be higher.
As desired, or?
As desired. Well, per manufacturer. And epoxy standards are usually in the 2,000 range. So we think it's our fabrication process. So we think it's the cure. Actually, the professor thinks it's the curing time, and temperature. So we think a hotter curing will lead to like a more compact formation of the cross-linking. So we think that might lead to a more dense structure. And this is the neat epoxy. And this is of the mechanical testing of the nanocomposite, which was slightly higher, not much in this area, actually, I think. Yeah, it's very slightly higher than the other ones. And it should be a lot higher, but what we need to do is incorporate it better into the epoxy, because right now it's similar to just putting dust in there and forming an epoxy. There's no actual chemical bonds in there. It's actually just another material in there. So we want to find a way to actually chemically integrate it in there. So this is the future work, what we're planning on doing. We want to modify the surface with the silane, big fancy word right there. And once it's basically once we attach this molecule to the nanotubes, and when it cures, it'll actually take place in the cross-linking so that the nanotubes actually become part of the epoxy. So the properties are chemically and physically transferred to the composite. So basically this is the chemical we're attaching right now. And it's a long process, it takes like 20 hours. You have to boil it like at 120 degrees for 20 hours. And we evaporate it. It's a constant evaporation. It evaporates, falls, evaporates and falls, and you're left with a pure substance. So basically, yeah, these are the tubes with the chemicals on them. This is the silly drawing of the epoxy. And then everything's entangled right here, so everything's like together. And this is the process that we did. We actually did this day before yesterday. We get the silane, we mix it with the nanotubes, we sonicate it for a while to get it very well dispersed, and then what we do is we call refluxing for 20 hours at 120 degrees. And then we just filter it and wash it to make sure we're left with just nanotubes and just the silane. This is the future work. This is what the end game of our research is. We basically want to fill the nanotubes with the epoxy parts themselves, so that way when they break, there's like a self-healing, the agents are released. And so this is what we want to do. We want to put the nanotubes in a solution of diluted epoxy, and then we want to vacuum it out, and so theoretically they should be able to get shoved in there. And other people have already done this type of work. There's lots of cancer drug research done in this field, because these tubes they're inorganic and they're non-toxic at low doses. So people are putting drugs in them and then delivering that to cells, and then it's released like it's a mini capsule. And so we want to try that with epoxies. So basically, in a solution, we vacuum it out, the stuff's left in there, and we wash it out. And this is kind of like the mechanism. The red one would have the curing agent, the yellow one would have the epoxy. So when a crack propagates, it releases this fluid, and it hardens on its own. So that way we have a self-healing composite. And that's the ultimate end game of our research. And I went kind of fast, but do you have any further questions?
How long have y'all been working on this?
We started at the beginning of October. So actually, it's kind of the chemistry is real quick, because it's basically mix and stir and take some measurements, but it's a very delicate process. So many factors: the temperature, the degassing, the amount of solvents in there, and it's a very very tedious process. But it's very very promising. There's a lot of things in this field. Our first thing is to try to get different types of epoxies in there, and then our next step would be to try other nanomaterials such as carbon nanotubes. We want to try to put those in there because they have great properties. We want to try to put nanotubes inside these tubes and put them in there, because the deal with nanotubes, they're very hard to work with, they're very hard to disperse, so you have to do things chemically to them. But when you do things chemically to them, you hinder their properties. So putting them in here, we would preserve their properties and still have a very strong structure. That's basically what we're trying to do. And there's a lot of work out there being done there right now. This stuff is fairly new. These tubes are just starting to be exploited as a new material because they're less toxic, or they're toxic at very, very high doses. But like anything, it's like you can take a lot of salt and it's toxic. And so but nanotubes are very toxic. Nanotubes are small enough to get into cells and kill them. And these stuff are relatively safe. And yeah, there's a lot of NASA work being done on this.
Do you know of any studies of different types of structures that would be stronger, or why particularly in tubes as a strong structure?
The thing that makes them strong is it's a small compact tube and the long length. So it's basically like putting kind of how they put rebar in cement. That's the kind of the type of effect they're going to. So the tubular structure, they're very rigid at those small scales. The very small scales are extremely rigid. And nanotubes are supposedly the strongest at that scale. Like nanotubes are like 100 to 1,000 times stronger than steel and very conductive. but those are very toxic. These are not as strong as nanotubes, but they're a pretty close second. Or not as close, but as far as non-toxic and natural. Like if this stuff were to break down and decompose, you're left with a natural biodegradable substance. Whereas if you use something else, it could potentially be harmful. But from this, personally, I would like to go from this to actually look into trying to put drugs inside them. Like you can fit all kinds of drug molecules. Like they do resveratrol, it's a cancer drug. And what they do is they use the same procedure that we had here, this right here, and they load the drug into there. And then once you do this process, you can do a second process, and you can actually cap the ends with a fluid. So when you enter it into the body's pH levels will kind of like react with the ends, and then you get a timed release, a slow release. And so that could be possible here too, to have some kind of a timed release right here.
So rather than being a cement or a resin harder than be some kind of
Exactly.
resin.
So basically, if there's a small crack, because usually when you have plastics and stuff, when plastics and epoxies fail, it always starts at the micro level. You have a micro fracture, and then it propagates. And then when you have the breakage, there's already been a lot of cracking that you don't see. At this level, when you have micro fractures, we're hoping to stop it there at the micro level, so it actually adds strength, so it'll buy some time on a piece or whatever.
Earlier you mentioned something about tetrahedrals and octahedrals.
Yes.
Can you kind of mention about that too?
Right here, let me see, it's a tetrahedral with the silicon and the oxygen. So right here we have oxygens. Actually, it'll be better in this picture. So the yellows are silicon and it says the gray, but basically every silicon you would have would be surrounded by 4 molecules. So it gives you a tetrahedral, basically like a tetrahedron with the silicon atom at the top. And that's a very rigid atomic structure. And because of the angles of the structure, that's what allows for this curve, because it's just tetrahedron, tetrahedron. And then the other one's octahedral. So basically you have an oxygen molecule surrounded by a bunch of aluminum, and that also has a curved shape. So that's how you're able to get that nice curved, continuous structure.
Okay, that makes more sense to me.
Yeah.
Now I see the triangles, because we were always told that triangles are the strongest shape.
Yeah.
Right, so here you're making triangles, tetrahedrals, and the octahedral are all triangles.
Yeah, and it's also with chemicals and molecules, it's based on like bond angle and strain angle, and it's a triangle shape.
So they really are that perfectly round?
They're not that perfectly round, but they're pretty close. That all the models like these right here, I mean, that's as perfectly straight as it's gonna get.
Okay.
But
Do they look pretty straight?
Yeah, they're very straight. That's about as straight as you can get. They're pretty chemically straight, and they've done some modeling on them. And they're some researchers in, I think, Berlin have actually been able to recreate them in the lab using various processes, and they're able to see that they're pretty straight. And they do a X-ray diffraction. Basically, they shoot X-ray at it to see the crystal structure, and that's how they know they're pretty straight in the internals.
Can you go back to the other, just to kind of relate more math for those who aren't seeing the math yet. This kind of reminds me of like wreath products, the small circular ones, and relate that to graph theory, and also with networking and stuff, and also relating the geometric structure of these things in terms of their strength. It seems like there is a lot of actual mathematical details that could go behind this. So when I was looking through your slides, it's like, oh, that looks like graph theory, that looks like differential equations, that looks like linear algebra. And so it's really cool that it's there.
Yeah, it is. Another interesting thing on these is that they're electrically neutral, which is kind of odd since they have so many, they have aluminum, which can be very ionic, and silicon as well. But the spaces in here, the electric field in there, they all balance each other out. So that their shape, kind of makes them all electrically neutral. And so that's a pretty interesting property. And you can also do things to them to like these oxygen atoms or hydrogen atoms here in the center, you can remove these and then give this like a slightly negative charge, and then you can kind of put a negative ion in it. And you can kind of calculate or predict the charge that will be based on the length, how many molecules or atoms you think will be in there per that length, and the charge per molecule, and add all that up. So yeah, it's definitely an interesting field because they have a specific structure, so you can do a lot of calculations. There's not going to be much variation when you get pure ones of these. It's very interesting. And yeah, the vector area is actually pretty interesting too. Like you can imagine these right here cut in half and split open. The way you roll them up, if you roll them straight, which is perpendicular, you get one. If you roll it at a certain angle, you get another one. And there's where that angle lies, you get certain connections. You get certain electrical property. It changes electrical property slightly.
Is it sort of indexed or at a certain point it switches, or is it like at every different angle?
No, there's a specific cutoff. There's three types, and it's perpendicular up to that angle, and that angle up to 90, and then you just basically that's all. Yeah.
Bifurcation or something.
Yeah, and it's very specific because at certain angles, these molecules only line up at these angles because of their bond angles, their bond lengths, and their electrostatic properties. They'll only line up in those ways. Yeah.
I just have a quick question about the stress and strain slide that you had there.
Yes.
You have some computer simulations, right? Or are these just tests on the nanotube structures that you build?
These are tests of the nanotubes in the epoxy. Yeah, so basically it calculates the Young's modulus, the elastic modulus, the tan delta, which is a function of those, and there's like 7 things that it calculates, but these are basically the loads that we care about.
Because I think if you get these numbers for the stress and strain, then you can kind of build a continuum mechanics model for it.
Yeah.
Maybe do simulations that would tell you, they're layering things.
Mhm.
People do this with composites, right?
Yes. The different layering.
They create the simulations before they do the testing.
Mhm.
It's much cheaper, right?
Yes, yeah, it's a lot cheaper. And that's one of the good things about these Halloysite nanotubes. They're relatively cheap, so we have some play in there. But that's how our professor knew that these were low, because he knows from what he studied that they should be at a certain level. And that's how a lot of these companies that we get this from a company that makes it based out of Houston called Momentive, and they make a lot of aerospace and industrial grade products. And they have a good research team, and so they have accurate models and predictions of what these should be, and so that's how we know low. As far as on that level, we're not doing any modeling, but there's a lot of research that we're looking at too, because it is good to know that way we have an idea. And yeah, it's basically how we know where it should be.
I mean, these numbers, right, if you're testing it, can actually then go back to the people who are running the simulation.
Exactly, yes.
If they don't know these numbers, they
Yeah.
can't do anything, right?
Yes, I've actually emailed these numbers to Momentive because saying, is this right for what we're doing, our parameters? We're waiting to hear back because they do the modeling. But yeah, it's very important for that too. Because when you look at research, that people that do modeling, their test numbers, they have tons and tons of files of testing that just get recycled, and so they know. And yeah, it's like a continuous process. Give and take. It's very interesting. It's a very interesting field. And it's actually pretty cool. I actually had a couple just chip samples that I could pass around. This one right here is just regular epoxy by itself, and this one actually has the nanotubes in it. And this has 1% of the nanotubes, and it's a plastic-like structure. When you have to pass them around, they're safe. Relatively safe. They have sharp edges. I did research last summer with the composites with nanotubes, and none of that's safe. That stuff is highly, highly toxic. They're very strong and they have very great properties, but they're very, very toxic. That's what they're trying to get away from.
So I'm trying to see it. So,
Yeah, they're tiny. They're so dispersed in there that they just cause a light color change.
So just okay, I see what you're saying. So you're not gonna be able to see a tube.
Yeah, you won't be able to.
You just think about that it's a color change.
Yeah.
It indicates that it's there.
Exactly.
Okay.
And if you were to see something, what you would see is an aggregate, and it would be like about I think like 1,000 of them together, you might be able to see as a tiny dot. But we're not sure if the color change is from impurities mixing in there, or it's optics, just the light, actually change the color part. That's something we're looking to. The XRD should tell us that, and the FTIR should tell us what other chemicals are in there. It's pretty interesting work. Yes.
So you're working on this as an undergraduate?
Yes.
And are you writing like an honors thesis on this or anything?
Not yet. We're planning on publishing by the end of the semester, or end of next semester. And so it's just me and him and the professor, I'll get to be on the paper, which is really great. But for later on, this is a very good start. Yeah. And the good thing about these tubes, they're biodegradable and they're non-toxic to the environment. So they're really, really, really helpful. A lot of government money out there for it too.
Well, thank Christopher Reyes again.